Type 2 errors. And basically with type 2 errors, there isn't much difference whether you're using a discrete or a normal distribution. I'll show you cases of both, however. So the idea here, if you remember, a type 1 error was where you were rejecting your null hypothesis even though it was right. Here, it's literally the opposite. You're accepting your null hypothesis even though it is wrong. And you could rephrase this as to say that you're rejecting your H1, your alternate hypothesis, even though that's right. And it literally means the same thing, because if you reject your alternative hypothesis, you're going to accept your null hypothesis. And if your alternative hypothesis is right, then obviously your null hypothesis is wrong. So you can rephrase it. And again, with questions, one particular type of question would just be to explain what is meant by a type 2 error. So again, if you take the type of questions that could come with this, so one is just to explain, and in this you have to be careful to explain in context, as I explained. And context is basically the same explanation I gave in the video about type 1 errors. The second thing that they can ask you is they'll ask whether a type 1 error can be made in this particular case, or a type 2 error. And understand, type 1 errors can be made when you're rejecting your H0. Because only if you're rejecting your null hypothesis can you be susceptible to an error where you rejected it and it was right. However, if whatever test you were carrying out resulted in the null hypothesis being correct, then you can be at the risk of a type 2 error. So this is where you're accepting your H0. So when whatever test you carried out in the part that precedes this particular question, your depending on whether H0 was accepted or rejected, you can answer accordingly. And obviously they'll ask you, the main question is they'll ask you to find the probability of a type 2 error. Now the idea here, and with questions like this, they'll always give you the true value. So the true the true either probability in case of a binomial distribution, either true lambda in case of a Poisson distribution, either true population mean in case of a normal distribution, because this is what is respectively tested in a hypothesis test in the three distributions. In a binomial distribution, if you're carrying out a hypothesis test, you will always be testing probability. H1 and H0 will be in terms of probability, in terms of lambda for Poisson, which is also mean, and like in terms of population mean for normal. So they'll have to give you something. They'll have to either give you the correct value, the actual value for the for whatever thing you're testing for, either probability or either your mean, and you use that. What happens then? You use that value to calculate what do you call it? The probability of falling in the acceptance region, which is basically just not falling in the rejection region. So you use the new value and you then try to figure out how can you fall in the acceptance region of your original test. It might sound a little confusing when you say it like that, but hopefully I can explain it through these two questions and then it'll be clear. So let's look at this. So if you look at question 7, I don't believe we need to go through the entire question. So it says, in the past, the weekly profit at a store had a mean of 34,600 and a standard deviation of 4,500. Following a change of ownership, the mean weekly profit for 90 random chosen weeks was 35,400. And then you have questions, and we're interested in question in part 4. Given that the population mean weekly profit is now 36,500. Again, see, now they've given you the actual mean. They said like, okay, given that this is the real mean, now calculate the probability of a type 2 error. You can't just simply calculate it by your own initiative without having being given the true value. All right, so just to get an idea of what the question is saying, the question says that the store has, let's say, a mean of 34,600 and a standard deviation of 4,500. And again, the idea here is, even I'm not too sure how yeah, so we're not given the distribution of your overall population, but since your sample is 90, since n is greater than 30, you can simply approximate your sample mean and variance to be one of a normal distribution as per the central limit theorem. So that's fine. So you're given a particular mean and standard deviation, and the test that they're carrying out is whether mean weekly profit has increased. Okay, so the idea here, and they're carrying this test out here on a 5% significance level. So your H naught is that mean is just the same, and H1 is going to be how mean has increased. And again, in a normal case, this is a continuous case. You're going to be testing mean. So that's what you're testing over here. Okay. So 5% significance level. So basically, what's happening, if this is the original normal distribution curve, and because it's greater than sign, it's an upper tail test. And this would be your critical region. The probability of this particular rejection area being 0.05, because you have a 5% significance level. And the idea here is now okay, it's one more thing to add, and the mean here is supposed to be 34,600. Now they've given you that the mean is 36,500. So what's happening here is that there's another curve, very badly drawn, I know, and that has a mean of 36,500. And you want to find out the probability that that any part of this curve falls in the acceptance region of your original curve, because your original curve is where you're carrying out the test. So your new mean value could be this, that is your H1 could have increased, your H0 could still be false. However, you would still accept it if it falls in this particular region, because this particular region indicates that it still fulfills the new normal distribution curve. However, it can still fall in the acceptance region of the old normal distribution curve. And hence, if your value comes here, you would simply say, okay, it falls in the acceptance region, and that means H0 should remain the way as it is, and we'll just accept H0 even though H0 was incorrect. And so you just find the probability of this particular region. If you notice, so the Z value for this should be, I believe, 1.645. Let me just quickly, where's the MF9? Yeah. So if you look here, we're looking for 0.95, and the reason we're looking for 0.95 is because if you just draw it here, this particular area is like 0.05. For the Z value of here, you'll have to find the probability of all the probability behind it, which is 0.95, and through your critical values, the quick values given, you can find out, you can see that it's, if I can just write here, okay, it's not letting me write here, but okay, but it's 1.645. You can see that from your distribution table, right? So you need to find the probability in the new, using the new curve, that your value can be less than 1.645, but 1.645 is your z value. So you'll need to convert that into an x value using your old distribution curve, because it's the z value of your old curve, right? So z is of x minus mu over, let's say, sigma square upon n root, because again you're talking about sample variances, and because of that you have to convert your population variance into your sample variance, so you always divide by n, or if you have standard deviation you just divide by root n. Okay, so in this particular case, let me use a different color. So 1.645, you're trying to figure out the x value for this particular amount. No, I don't want to restart now. Okay, and the mean, the old mean that we're talking about is this. What was sigma? Okay, so your standard deviation was 4500 upon root 90 weeks, so n is 90, and using this you can figure out the particular x value, and that value is 35380. Now again, be a little clear what's happening. What we basically said that this is, let's say, your old curve, the old mean, and we said that if on the old curve with the old mean, any value of x that is less than 35380 would be accepted. Now we have to find out the probability that there would come a value that is less than 35380 in the new curve, which represents the distribution of your new, of the mean that you're given, the mean that is correct. So the idea here is that the new mean, where you have your new curve, that is correct, but even that has a distribution, and because of a distribution, there is a possibility that the particular value you get from your new curve is less than 35380. If it is, then it would be accepted by the old curve, and you'd simply deduce that that h0 is correct even though it isn't. So you'll now find the probability that x is less than 35380. However, you'd find this for the new curve, and if you do so, you'd find z, which is 35380 minus what is the mean of the new curve, 36500. So 36500, sigma square and all are still the same, so that's sigma upon root 90, and through this you can find z. Z is minus 2.361. You just pop that into your calculator, right? And what's basically happening in the new curve, you're trying to find this particular area. This is minus 2.631. So you use the symmetrical property of the bell curve. So this area should be the same as this area. Both the shaded areas are the same, and this is positive 2.631. So if you can find this area, which is phi of positive z, and subtracted by 1, it should be the same. So the probability should be 1 minus phi of positive z, which is the probability behind or less than positive z, which is basically like AS, normal distribution. So like, hopefully you guys know it. That gives you 0.0091, and that, ladies and gentlemen, is your type 2, is the probability of your type 2 error. We can also find it in cases of discrete distributions. Here we have a binomial distribution, which obviously is a discrete distribution. What's happening here is whoever this girl is, she wants to see if her dice is biased. So her h naught. Again, in binomial, you're going to be testing probabilities or proportions. So h naught is 1 upon 6, and h1 would be probability. So yeah, she tested die by 25 times. If it shows a 6 on 3 or more times, okay, so she's testing whether uh, the probability is greater than it should be, and that would indicate that the die is biased, right? And again, if you look at the question here, look at type 2. For type 2 error, they'll always give you the true value, or they'll always ask you to assume that this is the true value of the probability, or of lambda, or of population mean. So it's basically the same method every single time. So they'll say, okay, so let's assume that the value of p is actually 2.2 upon 3, and you have to calculate the probability of a type 2 error. Now, the idea here is that you use this new probability. So you use this, and you find probability of the acceptance region, or basically not the critical region. Now, I believe that you've already would have calculated the critical region in the above part. So I'll just go find that. And in part 1, you would have calculated this because it says that if it shows a 6 on 3 or more throws, she would have concluded that it is biased. So which basically means the probability of the rejection region would be x is greater than equals to 3, because she reject h naught and conclude that it is biased if it is 3, if it is 4, or if it is 5. Not more than that, because she only throws it 5 times, right? And you would have just used the old probability, and your number being n, 5 being n, to calculate the probability of the critical region, which you've done in part 1. And yeah, the probability of the rejection region is this. So basically, you just have to figure out the probability that this will fall in the acceptance region, except you need to figure this out by using the new value given to you of p. So you have to find the probability that x could be, let's say, 0, 1, and 2. So basically, probability that x is less than equals to 2, because again, this is discrete cases, so you'll only talk about integer values of x, and it can't go through 3, because 3, 4, and 5 are part of your critical region, your rejection region. So you'll simply find out the probability that x is less than equals to 2. N is given to you as 5 from the question. Your probability that you're using, sorry, p is the new one. It's 2 upon 3, which makes q 1 upon 3. So your answer would be 5C0, 2 upon 3, 0, 1 upon 3, 5 minus 0, which is 5. These two should just be cut to 1, if you pop it in your calculator. 5C1, which is 2 upon 3, 1, 1 upon 3, 5 minus 1, which is 4, plus 5C2, 2 upon 3, 2, 1 upon 3, 3. And this will be the probability that if you use your new p that is given, you can still fall in the acceptance region, which is not the rejection region. So you just pop this into your calculator, and you should get the probability of a type 2 error in a discrete case. And that is equals to 17 upon, sorry, not 18, upon 81, which you can write, again, just remember to round it off to 3 significant figures. That would be 210. That is your probability for a type 2 error. Hopefully this was helpful.